Logarithms are used to find out exponential variables. There is a new set of derivatives of logarithmic functions. Check them out here in differential calculus. Before we start with the different derivative formats for logarithmic functions, let's have a look at the different laws of logarithms. The first is the log of a product, which is the logarithm of the first term plus the logarithm of the second term. The next law is the logarithm of a quotient, that is the logarithm of x all over y, and this is expanded as the logarithm of the numerator x less the logarithm of the denominator y. The third law is called the logarithm of a power. Say we have the logarithm of x raised to n. This is taken as n times the logarithm of x. The other supporting laws are the log of a raised to x, which is still x, and a raised to logarithm of x, which is also x. Now for the pattern of derivatives of the logarithm. There are only two. One involves the natural logarithm ln of u, and its derivative is taken as u prime over u. Additionally, the derivative of log of u base a is m times u prime over u, where m is the logarithm of e base 10, and this is also 0.43429. The first example has the function y is equal to ln of the quantity 7 minus 3x. With the rule of u prime over u, we identify u from the function, and that is 7 minus 3x. U prime is then the derivative of 7 minus 3 times the derivative of x. The first derivative term is 0, and the second derivative term is 1, giving u prime as negative 3. Now place u and u prime in the pattern to get y prime as negative 3 over the quantity of 7 minus 3x. The second example has y is equal to ln of cx, where u is cx and its u prime is solved as c times the derivative of x, and that is simplified as c. So y prime is c over cx, where we can cancel out the c's, leaving y prime as 1 all over x, or x raised to negative 1. The next example is solved in two different ways. First is the conventional method of the function y is equal to ln of the quantity a squared minus x squared raised to 3 halves. U is taken as the quantity of a squared minus x squared raised to 3 halves. With 3 halves as the exponent, we solve for the derivative of u using power rule, where the detailed derivative of a squared is taken as 0, as a is constant, and the derivative of x squared is 2 times x times further derivative of dx all over dx. So u prime is negative 3x times the root of a squared minus x squared. Plug these expressions into y prime to have negative 3x times the root of a squared minus x squared all over the same quantity raised to 3 halves. And because we can reduce terms by canceling similar ones, we get y prime as negative 3x all over a squared minus x squared. The alternative solution is through the use of laws of derivatives. Let's check the difference of approach with the same example y is equal to ln of the quantity a squared minus x squared raised to 3 halves. With logarithm of power, we can take down the exponent to have y as 3/2 times ln of the quantity a squared minus x squared. Without any exponents in the term, we can work with u as a squared minus x squared, and u prime is the derivative of a squared minus the derivative of x squared. A being a constant will have a derivative equal to 0, and the other term is then worked out as negative 2x times dx all over dx. U prime is then simplified as negative 2x. With both parameters already determined, y prime is taken as 3/2 of negative 2x over a squared minus x squared, where the 2's are cancelled out, making y prime as negative 3x all over a squared minus x squared. Example 4 has the equation y is equal to x squared times ln x. Just for you not to get confused, check out that the term with ln is only a simple x. So the function's derivative can be solved by the conventional method, starting with the product rule. Y prime is x squared times the derivative of ln x plus ln x times the derivative of x squared. U is then x, where its prime is 1. So y prime becomes x squared times the reciprocal of x plus ln of x times 2x multiplied by dx all over dx. X's cancel out in the first term, and also with the dx's, reducing y prime as x plus 2x times ln of x. Next is the derivative of y, which is equal to the reciprocal of ln x. The problem can be solved as ln of x raised to negative 1, and by power rule, we have y prime as negative 1 times ln of x raised to negative 1 minus 1 times the derivative of ln of x, where u is x and u prime is 1. Y prime is then negative of ln of x raised to negative 2 times 1 all over x. So y prime is finalized as negative 1 all over x times the square of ln of x. The next example has the function y is equal to ln cube of x. The function can also be written as the cube of ln x, and with the cube, we use power rule where y prime is 3 times ln of x raised to 3 minus 1, and this is multiplied by the derivative of ln of x. Again, u is x and u prime is 1. So, y prime is solved as 3 times the square of ln of x multiplied by 1 all over x, or that is 3 times the square of ln of x all over x. The next example involves the equation y is equal to sine of ln of x. With the outer operation as sine, we have y prime as cosine of ln of x times the derivative of ln of x. Again, u is x and u prime is 1. So y prime is cosine of ln of x times 1 all over x. And we simplify y prime as cosine of ln of x all over x.